All right, welcome to The Explainer. Today, we're going to crack a code. Not just any code, but the code that runs, well, everything in our digital lives. It's a secret language that your phone is speaking right now that powers the biggest supercomputers on the planet. And here's the crazy part. This entire complex language, it only has 2 words. Yeah, you heard me right. Just 2 words. So, how is that even possible? How do you build this massive digital universe we live in, with all the streaming videos, the games, the endless data, with a vocabulary a toddler would find limiting? That's the huge mystery we're going to unravel today. Well, the answer actually starts with something super simple, something you use every single day, a light switch. Think about it. It can only be in one of 2 states, right? It's either on or it's off, and that's it. For computers, we just give those states a number. We say on is 1 and off is 0. And believe it or not, that simple idea, that's the foundation for everything. That's the entire binary world right there. Okay, so let's zoom in and focus on just one of those switches. This single unit of on or off, you can think of it like a digital atom. It's the smallest possible piece. And it has a name. It's maybe the most important word in all of computing, the bit. Yep, a bit. And that's just short for binary digit. It's exactly what it sounds like, the absolute smallest piece of data you can have. Just a single 1 or a single 0. You literally can't get any smaller. It's the rock-bottom, fundamental, indivisible building block of, well, everything digital. So a really good way to wrap your head around this is to think of a bit as just a simple yes or no answer. Is the light on? Yes, that's a 1. Is the door closed? No, that's a 0. For a machine, this is just perfect because there's no confusion, no kinda, no maybe. It is one thing or the other. Totally clear. But, okay, you can see the problem here, right? You can't really do much with just one yes or no. I mean, how are you going to write your name or type a number, like, say, 27, or even just use a question mark? A single bit just isn't going to cut it. We obviously need more complex words. And this is where engineers had a really brilliant, but actually very simple idea. They thought, okay, if one switch isn't enough, what if we just line up a bunch of them together? And that simple idea leads us straight to our very first digital word, the byte. So they needed a standard. And the standard they settled on was to group bits into a team of 8. And this little group of 8 bits, that's what we call a byte. And that became the standard word for pretty much all computers. Okay, now get ready, because this is where the magic really kicks in. If you have a group of 8 bits, and each one can be either on or off, how many different unique patterns can you make? Well, the math works out to 2 to the power of 8, which gives us this number right here, 256. Just like that, by grouping 8 simple switches, we've gone from a 2-word vocabulary to having 256 unique words to play with. That's a game changer. And it turns out 256 is the perfect number. It's more than enough combinations to assign a unique code to everything we need. We're talking every uppercase letter, every lowercase letter, all the numbers from 0 to 9, and all the punctuation and symbols you can think of. It all fits. So here's how that actually looks. There's a universal rulebook, basically, called ASCII. And in that rulebook, every character has its own unique 8-bit code. So, for example, the pattern you see there, 0100001, that will always mean a capital A to any computer. Change just one of those bits and you get a B. Another totally different pattern gives you an exclamation point. By doing this for every character, we finally have a complete digital alphabet. All right, so we've got our letters, our digital alphabet. That's awesome. But what happens when we start writing, not just a single letter, but entire books or creating huge photos in movies? Suddenly you're dealing with millions or even billions of these bytes. We're going to need a better way to talk about these huge numbers. And honestly, it's the exact same logic we use all the time in the real world. Think about it. You wouldn't measure the drive to another city in inches, right? That'd be crazy. You use miles or kilometers. We do the exact same thing with data. We just group the bytes into bigger and bigger chunks to make it easier to talk about. So let's just quickly walk up that ladder. We start with 1 byte, which is basically 1 character of text. Now group about 1,000 of those together and you've got a kilobyte. That's like a short email. 1,000 of those gets you a megabyte, which is maybe one high-quality photo. 1,000 megabytes, now we're at a gigabyte, enough to hold a whole movie. And 1,000 gigabytes brings us to a terabyte, which is probably about the size of the hard drive in your computer right now. Okay, and here's a quick nerdy side note for you. I've been saying 1,000 just to keep things simple, but technically, a kilobyte is actually 1,024 bytes. So why the weirdly specific number? It's because computers are all about the number 2. They think in powers of 2, and 2 to the power of 10 just happens to be 1,024. It's a funny little quirk that's a great reminder of the binary system running under the hood. All right, this brings us to the last big idea, and it's a really important one. We've talked about bits and bytes, but on their own, they're just stuff. They're raw materials. So what's the secret ingredient that turns them into something we can actually understand? This is the huge difference between what we call data and information. Take a look at this. This long, jumbled mess of ones and zeros. What does it mean? Nothing. On its own, it's completely meaningless. It has no context. This is what we call raw data. I love the analogy of a pile of Scrabble tiles just spilled on the floor. All the letters are there, sure, but they don't spell anything. It's just a mess. So for that raw data to become something useful, it needs one crucial thing: context. It needs a rulebook. The computer needs instructions, like a dictionary, that tells it how to make sense of that long stream of ones and zeros. And so when we give the computer that context, when we tell it, hey, use that ASCII rulebook we talked about earlier, all of a sudden, that meaningless jumble of data completely transforms. That string of bits suddenly becomes a word we can all read. Hello. The data has now become information. And really, that's the main job of a computer. That's what it's doing all day long. It's taking in raw, unstructured data, all those ones and zeros, and it applies a set of rules to process it. And it spits out structured, meaningful, useful information that we as humans can actually understand and work with. So let's recap. We've cracked the code, we've learned the secret alphabet of computers, bits and bytes, we've seen how raw data gets turned into real information, but that leaves us with one last really cool question, doesn't it? We know the alphabet now, but how do we start writing sentences? How do we string these things together to give commands and actually tell the computer what to do? Well, that's a much bigger story for another time.